We did our indie lab on the pretty much the math behind what notes sound good and bad together.
Okay, so yeah, you want to do this one?
Yeah, we just wanted to know like why things sounded good, why notes sounded good and why notes sounded bad. We just kind of played notes. Okay, we played it into odd. Yeah. Okay. So we thought that they sounded good and bad for a reason, that there would be like mathematical patterns and it wasn't just random.
Oh, and by good and bad we mean like intervals, like two notes played together. Because sometimes, depending on the note, like two notes will sound good together and two notes will sound bad together. So that's what we mean.
Yeah. So Sam played on his oboe the like notes from C, 1C to 1C, so that's like a full octave. And then we did it in Audacity, and what that does is it'll record it, and then when you zoom in, it has like the waves and stuff, so you can count the frequency if you do if you count the number of waves, and
then you have
that in respect to the time. Yeah. So that's how we figured out the frequency of whatever note he played.
Each note. So yeah, so that's what it looked like. But when we did it, the graphs, or like the graphs that Audacity made, look like this, where you can't really count like crests and troughs. So
but there were like patterns within the waves, and that's how we did it.
We noticed that there were like patterns. So each of these boxes is around like one parts of the pattern, and so we counted. So we thought that those would be like waves. So we counted how many of those there were, and then we divided that by the time, the time allotment, and then that gave us a frequency, and then we just checked to see if it was near the actual frequency, and it was. So then we kept using that method. So, okay, so this is our data table, our first data table. It's all our frequencies.
So those are measured frequencies, not desired frequencies?
Yeah, these are measured.
Okay.
They're really close to the desired.
Yeah, like this one is actually right on. So then we made a graph of frequency versus the note, but we couldn't make like an equation or anything because we can't assign like a number to the notes. It would just be like 1 or 2 or 3 or something. And that's not like, I don't know, you just can't make a graph with that. You can't make an equation, I mean. But we noticed that it wasn't necessarily linear. So that led us to believe that the difference between notes is based on ratios rather than like the same number each time.
Because the difference between the notes kept getting bigger the higher the notes were.
Yeah. So then we made a table of half steps and the ratio. A half step is like the smallest distance between a note. So like if there's a note and then the note just above or just below it is 1/2 step away. And so what we did was we divided the frequency of the top note by the bottom note for each half step. And so we got all these ratios. What we noticed was that some ratios were like simpler and cleaner and nicer than others. Like 2 was a really nice ratio. We also got 1.5 and 1.33, 1.25 and 1.2. And then so the other ratios obviously are not as like nice. So so we noticed that the simple ratios, they correlated with intervals that are like pleasant to the ear. And in fact, the 3 simplest ratios were for intervals of 4th, 5th, and octave, and those are commonly regarded as the most like the easiest intervals on the ear because they're actually called perfect intervals, which I thought was interesting because they happen to have the simplest ratios. And then also, so we said these 5 are the simplest ratios. These 5 intervals had the simplest ratios, and the most pleasant interval was in the octave, which had the simplest ratio among them. And then a minor third was it had the least simple ratio out of this group, and it also happened to be the least pleasant sounding interval out of this group. But it sounds more pleasant than than like 11 half steps and stuff. So yeah. Since we noticed relationships between frequency, like ratios between frequency, then we wanted to analyze how that related to wavelength. And so since wavelength is velocity over frequency, when we assumed that the velocity of the sound was the same because we were playing on the same instrument, everything, in the same room, everything. So since they're inversely proportional, we can say that the ratios are inversely proportional too. So we just flip the ratios. So if like the ratio of the frequency of the top note to the bottom note for a fifth is 3/2, then the wavelengths of those notes from the top note to the bottom note will be 2/3. And so with this, we notice that the smaller the numbers are in the ratio, then the more frequently the waves meet at an amplitude of 0. So like this one, I think this one is a ratio of 2/3. So like the red, the red is, the red would be the 2. So there's like 2 wavelengths, and then the blue is 3, and it goes 3 wavelengths. And so they meet up after like 6 of these I don't know what to call. I guess I would just call them units. I mean, obviously they meet up in the middle, but we're talking about where they meet up back when they start over again. And so to get that number, you would multiply the top by the bottom, which is like the least common multiple of the two numbers. So we thought that the simpler the ratio, like with the smallest numbers, then it would have the least common multiple. And then also, so like this, like 11 half steps, 1.935, that would require, like if you were to put the ratio in a fraction form, it would require like really big numbers on the numerator and denominator, because it's not like simple. So that's those numbers' least common multiple would be a lot higher, and so the waves would have to go a lot farther to meet up again. So we thought that we thought that the more frequently the waves meet up at 0, an amplitude of 0, then the more consonant the interval sounded. So that was our analysis.
We got really low error for all of that stuff, or all of the notes that we played.
Yeah. So our little method of counting patterns was good.
And you're good at playing the oboe.
It's the best in Missouri.
Dang.
Okay. So yeah, our conclusion, intervals sound better, more consonant, the more frequently the wavelengths meet, and the amplitude of 0. And so that goes along with the frequency. And the simple ratios have the wavelengths meeting frequently, or the waves meeting frequently, and the more complicated ratios have the waves meeting less frequently. So, also another thing is, so a minor third is like a kind of interval, and it's kind of like an evil interval, like that's in the West or whatever, that's what we associate with an evil sound. And we notice that it's that ratio for that interval is kind of in between I talked about this earlier, but it's like in between the simplest ratios and the most complicated intervals or ratios. So we thought maybe the evil sound comes from like in between, like it's not entirely consonant, it's not entirely dissonant. So I think that's it. Okay.
We have time for one question.
How did you get so good at playing
Look at that.
I want to
What's
let
your
Leslie play Oba.
Do you have a question?
Did you choose that background to be really simple because your title was about simplicity?
Yeah.
Ooh, well done.
Billy also came up with the name. Simplicity sounds good.
Could you go back to the all the notes and their ratios, the calculation there?
Yeah.
I was thinking as you were talking about notes that notes are an artificial construct that you would say that there are 13 of them or something, or 12 in an octave. Yeah, this is great. So those other ones must also be fractional relationships, I presume.
yeah.
But they're just unpleasant fractions?
Yeah.
So a person could look up what those ratios are supposed to be and compare your numbers. And then we just see. I would be interested, like if you wanted to go further with this, I'd be interested in figuring out what those ratios are and why those ratios have those relationships and why those are declared the notes in the West and what about the notes in the East. You know, I mean, they have a different set of notes that they can work with, right?
They have.
In Eastern music?
They just like, I don't know, it's structured differently.
Oh, okay.
I don't really know how it works over there.
Well, if you're interested, that could be next semester. This was really neat. Thanks, guys.